Okay, so we have here the list of all of the various reactions that we have learned so far in this class. Some of them require a catalytic acid. Some of them require a catalytic base. Some of them have carbanion intermediates, carbocation intermediates. I know that specifically the carbanion and carbocation intermediates has been a homework question before. So that kind of organization of the reactions will help you remember the reactions and remember the important facets of the reactions. So we'll start with identifying which of them require an acid. This list is very small. Can anyone name one? Yeah. Amine hydrolysis is one of them. There's another one that I'm looking for. Yeah. Transamination. In both of these, we have a catalytic acid. When I say catalytic, what does that mean? Claire? Yes. So when something is catalytic, it means it's reusable. So like an enzyme serves a catalytic purpose where it can do the same reaction over and over again. So the reason why I haven't listed acid-base chemistry in this requires acid is because you won't end with an acid. You'll instead end with the conjugate base of your acid, or you'll end with a new acid. Are there questions on this? How I determined this? Why isn't the reaction included? Why is this reaction included? Carmen? So transamination, what does an imine look like as a functional group? Yeah, so we have a C double bonded to an N. And so a transamination is where we're going to change that nitrogen out for a different one. So you can recognize transamination reactions because they'll start with an imine and an amine, and they will end with an imine and an amine. But they will be different than your starting one. So if our imine had R1 attached and our amine had R2, at the end of a transamination, R2 would now be in our imine and R1 would be in the amine. Does that make sense? Yeah. Other questions? Yeah. Mm-hmm. It's not catalytic because your H plus will add to one side of the alkene and the Br minus or Cl minus or whatever else is the other half of your acid adds to the other side of the alkene. So we're not able to reuse that at the end. Other questions? These are good questions. Yeah. Yes. I can see where you're coming from. And this is a question worded by me, not by Dr. Begley. So he would probably be more careful with the wording. And if it was worded like how I have it worded, an acid-base reaction would definitely get you at least partial credit, and you could probably argue up. Yeah. Mhm. Yeah, yes. It's like a substitution in that way. Other question. Great. So next we can identify the reactions that use base. We have one reaction where base is catalyzed by base is in the name of the reaction. Yeah? Yes. So one of our eliminations is E1CV, where the CV stands for catalyzed by base. Great start. What are some other reactions that require acid or base? Yes, aldol addition. Is that the only aldol reaction that requires base? I see you shaking your head. Condensation too, yeah. What else? Not quite. Please. I think that's a pretty good list. Are there any other options you guys want to run by? Yeah? Reverse aldol. Any other ones? Cool. Those are all the ones on my list as well. Are there any questions about this? About any of the reactions that are up here? How do we feel about this type of question? Asking about like details in a reaction. Thumbs up, middle down. Okay, a lot of downs. What's your question? So thinking about our curly arrow mechanism, on my study guide sheet, I have like in pink written requires acid or base. And when you walk through your curly arrow mechanisms, you'll see that it requires some kind of acid or base to help protonate or deprotonate the molecule at certain steps in the reaction. Other question, comments, concern? Yeah. Mhm. That would be fine. What's up? Mhm. Let me look at what you're talking about. So that does require a base. In this situation, it requires a base. It may not necessarily always require a base. That'd be fine. Other questions? So next one is identifying which of the reactions have a carb anion intermediate. What is a carb anion? Yeah? Okay. Yeah. Carbon with a negative charge. So again, this is where we're looking through our curly arrow mechanisms and finding which ones have an intermediate where we have a negative charge on a carbon. Yes. Oh, sorry. Thank you. So which of our reactions do we know needs a carb anion intermediate? And there was a homework question that asked this exact question. So good to know. Does a carbocation or carboanion? It's more of our recent reactions. Aldol? What else? Yeah. Would you be doing a nucleophilic or an electrophilic addition? Yes. Any other ones? Claisen? What else? Mm-hmm. I have two more on my list. Reverse aldol? There's one more. And we've actually already mentioned it in a different question. Any old E1 or a specific E1? E1CB. Those are all the ones I had on my list. Are there questions about how we got to these answers? Okay, we'll move on then. What is a carbocation? Put any old positive charge on a carbon. So which of our reactions can go through a carbocation? If E1CB goes by anion, What's up? I wouldn't worry about that. So, carbocations. What's the major difference between E1 and E1CB? How does that change the mechanism reacting with the base? So when we have base catalyzed elimination, we have a carbanion intermediate. If we don't have the electrons from that base, we have a carbocation intermediate. The mechanism for E1CB was like the first question on exam 2. So I would say review that, and you can, like, you have your copies of your exam, so you can see how you did, what you put down, where you got maybe partial credit, where you didn't get credit, where you did get credit. I would say knowing that mechanism is important. What are some other reactions that we've learned that have a cation? Yeah. SN1. What's up? Correct. So other reactions that have a carbocation. What is one major cation we work with a lot in this class? Not necessarily a carbocation, but a general cation. That is one, but not the one I'm fishing for here. Yeah. Yes. What do we call this? Like a fancy name or a very fancy general name? Proton, yes, but not what I'm looking for. To describe if it's electron rich or electron deficient. Electrophile. Yes. Not the one I was fishing for, but a correct answer anyway. That is the one I was fishing for. Those are the 4 that I have on my list. Does anyone have other ones? Okay. Do you have questions on this? Yeah, what's up? Yes, because carbocations are inherently electrodeficient, and a base usually has a lone pair and has electrons to share. Other question? So the last part of this question I had was for each of the reactions, give an example and identify what type of bond is made or broken. Rather than spend time drawing all of them out, I'm just going to go by name. But if you need a breakdown, I could also do the words for like the starting material or draw out specific ones? What's up? You have had a homework question where you are just supposed to give an example off the top of your head. So I would anticipate a question like that. So, first reaction, acid-base chemistry. What kind of bonds are made or broken there? Any takers? What's the main gist behind acid-base? Proton transfer. So you are going to be making some kind of bond and breaking some kind of bond with proton. Addition reactions. Well, addition to alkenes. What kind of bond do we break? A double bond. I'm going to write it as a pi bond. And then what kind of bonds will we make when we do an addition to an alkene? Yes, sigma bonds, but what atom will always participate? Carbon. Next up, we have electrophilic aromatic substitution. What bond do we most often see broken? A pi bond gets broken in the process, but yes, carbon hydrogen. But the pi bond gets restored by the end. So that's why I wouldn't consider it a true answer here. But you are right. A pi bond gets broken within the process, and then we have the deprotonation that puts it back. What kind of bond will get formed? Yes, but we have a really common electrophile that we use. So if that was our electrophile, what kind of bond would we make? What would our X be? C, because we would attach to this carbon here. So with nucleophilic substitution, what kind of bond will we break? Carbon to what? It could be to hydrogen. Will it always be hydrogen? What else could it be? Yeah. What else could it be? Will it always be hydrogen? What is our most common example of nucleophilic substitution? Is hydrogen a nucleophile? So, bromine is a good one, is a good example. What is bromine, a nucleophile or an electrophile? We're going to break a C nucleophile bond. And what will we form? It is the same. We're just doing it to a new nucleophile. And so sometimes our nucleophiles can be bromine, they can be cyanide. So we could see carbon-carbon bonds formed, we could see carbon heteroatom bonds form, carbon halide bonds form. There's a lot of options here. So, elimination reactions. What kind of bonds do we see broken? That is the bond we form. So we form a pi bond or a double bond. But what do we have to break in order to form? Exactly. So we'll have that carbon nucleophile, and usually it's a CH bond as well. What's up? X I use as like anything. So could be a nucleophile or an electrophile. Because with addition to alkenes, sometimes if you're doing electrophilic addition, it'll be C to an electrophile. So CX is like X is anything, and then nucleophile is like a more specific subset. So next we have redox reactions. These ones are a little bit more complicated because we have a wide variety of redox reactions. What are some examples of bonds that we can see formed? What are some classic examples of oxidation? Those are cofactors for oxidation. But what kind of reactions can they catalyze? Like specific examples of redox reactions. There's two sets of three that are very, very common. Does anyone know what they are? Yeah. That is definitely one. It's not one of the more common ones. So you wouldn't be wrong, but it might be easier to memorize. What's up? Yes. Yes. So we have alcohol to aldehyde. Do you know what happens when we oxidize an aldehyde? And so we can take it even one step further to a carboxylic acid. And so in this direction, it's oxidation, and in the reverse direction, it's a reduction. So in an alcohol to an aldehyde reaction, what kind of bond are we making? Between who? What about when we go from an aldehyde to a carboxylic acid? What's the major difference between an aldehyde and a carboxylic acid? An oxygen, and we have to make that bond. As we go from this to this. Questions on what I've talked about so far? Yeah. Forming them. Yes. In acyl substitution, what kind of bond will we make? What happens in acyl substitution? What do we need as our starting material? We'll need some kind of carbonyl. Is it enough to just have 2 carbons on either side, or do I need more? What kind of more? I'll make it an amide. If I was doing an acyl substitution, what part of this am I substituting? The NH2. So I'll break my C heteroatom bond. Because we could have NH2, we could have OH, we could have sulfur, we could have phosphate too. Nope, it could be SH or OH or, yeah. So if we're breaking this carbon heteroatom bond, and it's a substitution reaction, so we're just substituting, what kind of bond will we then make? Yes. We'll form a bond between carbon and a new heteroatom. What kind of bond do we make in an aldol addition? Who participates in an aldol addition? What is our starting material versus our product? A base is part of our catalyst, but what is it catalyzing? Yeah, 2 ketones. What does our end product end up as? Them together. How are they connected? Double bond and condensation. We'll do that next. It is a carbon-carbon bond. Because we're going to attach one of these carbons, one of these carbons. So now, aldol condensation. What is the first half of aldol condensation? Yeah, it's basically just aldol addition. So we'll still have that carbon-carbon bond formed. But how does condensation go beyond aldol addition? Makes double bond. Reverse aldol. We'll focus more on, what's up? Yes. Which bonds will be broken? Mhm. Other questions about the reactions we've talked about so far? Yes. Is CH the only kind of bond broken in a condensation? What else is broken? Carbon in. Yeah, exactly. If we're going to form that water, we have to get that oxygen from somewhere. So reverse aldol reactions, what kind of bonds are we breaking? Because in a reverse aldol, our bigger step is the breaking of bonds rather than the formation of bonds. If it's the reverse of our aldol addition and we form carbon-carbon bonds in aldol, what do we break? Carbon-carbon bonds get broken. And we will form the carbon-hydrogen bonds. So, Claisen reactions. What's up? Yes. Other questions? Okay. Claisen reactions. What kind of bonds are we breaking and what kind of bonds are we forming? Breaking or forming? Is that the only kind of bond we break? Mhm. So what kind of bonds do we form? Carbon-carbon. What else? Oxygen-hydrogen. Okay, last set of reactions here. We have imine formation. What kind of bonds are we breaking versus what kind of bonds are we forming? Yeah, it gets formed, but then it's broken at the end to reprotonate the alcohol that comes off of the two molecules joining. So you could put base proton in both your broken and formed, but it doesn't really stick around for the whole reaction. Other questions? Yeah. A carbon oxygen bond is not. Oh, okay. I see what you mean. Like the pi bond. Yeah, I wouldn't list it here because it's not really a new bond. It's kind of just you have the tetrahedral intermediate and then it collapses again. Yeah. What? Yes. What's up? Mm-hmm. Always go for visual over words. So pointing at the bond formed rather than saying this reaction would form a CC bond, draw out the example and show the CC bond form. You wouldn't have to do curly arrows. You could just do starting material product and not the intermediates. But if you had a question like asking for carbanion intermediates or carbocation intermediates, it might be helpful to draw out the curly arrows where you then reach that intermediate. Other questions? Okay, imine formation. What kind of bonds are we breaking and what kind of bonds are we forming? Mm-hmm. What is that pi bond between? Mm-hmm. What is our major form bond? Single bond or double bond? Questions on this one? What's up? Yes, so you could, so it's, you have the tautomerization. So it's like you're breaking and forming the proton bonds. So I wouldn't include that in the like overarching process. Mm-hmm. Yes. Mm-hmm. Okay. Transamination. What kind of bonds are broken? Those are our starting materials. What parts of them will break and will crumble? Between who? DNA. And what bonds do we form? Transamination is a lot like substitution in that we are substituting the nitrogen of this imine for the nitrogen of this amine and all the things that are attached to it. Final one. Amine hydrolysis. What bonds are formed versus what bonds are broken? Between who? Mm-hmm. What's formed? Or question? From the acid or from the amine? My answer will depend on which proton you're talking about. Yes. So we could count that one. Yes, it might be easier that way for you guys. Mostly these questions or these kinds of questions will look at major bonds formed rather than minor bonds. And major bonds is really anything that is like carbon and something else. And then minor bonds would be most of your like protons moving around. Yes. Those are all the reactions that we have in class. Are there questions about specific aspects of this? Yeah. What do you mean the in-between steps? In this direction, it's oxidation. In this direction, it's reduction. So I wrote CO with that one because we formed this bond. Between the carbon and the oxygen. Then we form this one. Okay. Other questions on this? Okay. The next practice problem I had for you guys was about cofactors. But I got the vibe that people did not feel very confident about cofactors more than they don't feel confident about other things in the class. Is this true for a wider audience? Okay. We're going to do a cofactor crash course. So this will be more lecture style than like asking practice problem questions. And then we'll go through those practice problem questions. So cofactors, why are they important? Why do we care about them? They're used in enzyme catalysis. And when an enzyme catalyzes a reaction, it can basically take what was once one really high energy step and turn it into many low energy steps. And that helps reactions that maybe aren't thermodynamically favorable to still happen. And so these cofactors usually act by helping to stabilize some kind of charge or providing some other help. And so an enzyme is a very complex multi-peptide sequence that has been folded in such a specific way that you have an active site. And the active site is like a small part of the enzyme where you actually have the chemistry happening. And that active site has gone through many, 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 many decades and eons of evolution to be very specific. And so these active sites will have a very organized layout that will have amino acids that can serve as an acid if we need it, a base if we need it, nucleophile if we need it, an electrophile if we need it, or it can just be a counterion to keep things stable in a brief intermittent period. Amino acids will often serve as these acids and bases, but sometimes we need something a little bit more complex. And that's where we can have these cofactors come in. We have a lot of cofactors that exist in general, but we'll talk today and in our course about only a few. You should hopefully at this point recognize the names of these. From our various lectures. So I'm going to approach this one by one. TPP, the full name for TPP is thiamine pyrophosphate. And a lot of times with cofactors, it will have a big complicated structure, but only a little part of it will be actually important to what our chemistry is. And so with TPP, this is one of those cases where it has a big complicated structure where only a specific part of it is actually useful for our chemistry. This is the entire structure of TPP. Does anyone know what part of this molecule is the important part? Yeah? Not quite. Not quite. It's actually going to be this heterocycle in the middle. And so this proton will get abstracted or deprotonated by one of those active site residues. One of the amino acids in the active site can serve as a base and deprotonate there. And we get this structure as a result. And so I've modified how I draw this to kind of shorten the whole thing. When you see EI, that is an inorganic phosphate, it basically means this part. And then I've just turned this whole part into an R group. That way we can focus on the part of the molecule where our chemistry is really happening. The reason that we can draw it abbreviated like this is our resonance forms will only ever be localized to this ring. Does anyone see why? So our resonance forms can only go as far as our secondary electrons or our pi electrons can go. And we have this carbon here that has no kind of pi electrons that can allow resonance structures to move past it. And we have the same with this carbon. So all of our resonance structures can be compacted to just what is around this heterocycle. With our resonance forms, actually, I'll get to that later. Does anyone know what kind of reactions TPP is most known for? So, what you guys should most associate TPP with is the decarboxylation of alpha keto acids. Does anyone recognize that term at all, even a little bit? Yeah, I have not, or we have not ever learned what alpha keto acids are, but you do recognize the structure. We have two functional groups here that are right next to each other. What are those two functional groups? A ketone and a carboxylic acid. So an alpha keto acid basically means a ketone is next to a carboxylic acid. And when we are going to decarboxylate that, if we were to draw out our curly arrow, we would end with this carbanion. So that's the carbanion that we seek to stabilize with our cofactor. What is one way that we know of that we can use to stabilize a charge like that? A fancy word for spreading it out across the molecule. We can draw resonance forms where it's delocalized across the molecule. And if we can delocalize it across the whole thiamine molecule, that'll be even more helpful. So we can take our thiamine here. And our alpha keto acid. We have this nucleophilic site on our TPP, this negative charge on our TPP, that we can attack the electrophilic part of our carbonyl. Let me draw this. Oh, wait. And we can get this tetrahedral intermediate that then when it collapses can decarboxylate. So we can have our decarboxylation of our alpha keto acid using TPP. The main takeaway, or what I think you guys should study with this cofactor, is how can we get resonance forms from this structure here, or from this structure. And we'll know that TPP is most known for decarboxylating our pyruvate. That's what this molecule is called. It's the exact example that we have seen before, I think, in both lecture and homework. So, questions? Yeah. So you won't ever have to do an example of a reaction with a cofactor. That is not ever going to be expected of you because that would require also knowing what enzyme is helping this. The cofactor is not playing this role by itself. It had to be deprotonated by the enzyme. So you aren't ever expected to just list off a reaction that uses a cofactor. Other questions? Yeah. It could be that. It could be identifying the match the cofactor to the reaction catalyzed. Those are both kinds of questions that you have seen in homework in the past. No. What's up? Like structure, you do not have to memorize the structure of the cofactors. Other questions? Okay. We'll move to NAD and NADH. Does anyone know what kind of reactions you should think of when you are thinking NAD and NADH? Redox. Exactly. So NAD and NADH, they're the same thing, but in the reduced or in the oxidized form. And so the important part of the molecule to know is this. So this is NADH. And this is NAD plus. Yeah. You wouldn't be asked to identify the reaction type. You would be given like a reaction and asked to label the cofactor. Or if given a cofactor, can you say what kind of reaction it would be for? Other questions? Okay. We often see H plus. Less often do we see H minus. H minus is called a hydride. And that's where the hydrogen is not just moving itself, but it is taking electrons with it. And so with NADH, NADH is the reduced form. It has the electrons, it has gained the electrons. And NAD plus is the oxidized form. It has lost those electrons. And so NADH can help in our reduction reactions. What is an example of a reduction reaction? An aldehyde to an alcohol. So if we have our aldehyde here, and we take our NADH, we can take the lone pair on the nitrogen and move those electrons up where we get this intermediate, as well as our NADH has now become NAD+. And so it has lost electrons, it has been oxidized, and it has reduced our aldehyde to our alcohol. Questions on this? NAD+ can work in the same way, but reverse, where it will accept a hydride instead of hydride. I would say NAD is one of our more simple cofactors in comparison to all that's going on with TPP and PLP. Which PLP is the next one I'll talk about. So PLP's full name is pyridoxal phosphate, I think. You don't ever have to know the full name of these. The abbreviation is enough. And it's also known as vitamin B6. It, like thiamine, has a kind of big convoluted structure that we will pare down to just the parts that we need. So this is the entire structure of PLP. And PLP is most known for working with amino acids. There's two major examples of the reactions it can do with amino acids. One is racemization. And that is basically just changing the chirality of a specific center. The other one is decarboxylation. So you have two cofactors that can do decarboxylations, but one, you will see the pattern of the ketone next to a carboxylic acid, and the other one you should recognize will work with amino acids. So you should look for the carboxylic acid and the amine terminus, or amine functional group. Now, the reason that it works so well with amines, or part of the reason, is PLP really likes to make imine bonds. Ion bonds. We have this carbonyl group. And if you'll remember from imine formation, what we need is a carbonyl and an amine. Amino acids will always have an amine. Some even have an additional amine in their R group. So what we often see with PLP, and I think this is maybe what got people tripped up with the questions on PLP on homework 2, or homework 8, question 2, is our first step is PLP always comes bound to the enzyme. PLP is not often seen loose like this. Instead, it will be already have undergone imine formation with the enzyme, where now, instead of that carbonyl group, we will have an imine bonded to the enzyme or the protein. Usually it'll be positively charged. Now that we have the active form of our PLP, we can do trans immination because now we have an imine. And whether we're doing the racemization or the decarboxylation of an amino acid, we're going to have an amine. So with an anion potentially stabilized by the rest of the PLP structure, we can see decarboxylation here, or we could see deprotonation, which would allow for racemization, where we end up eventually with an anion here. And so in the same way that TPP has a carbanion that we can draw resonance structures with, PLP also has a carbanion that we can draw resonance structures with. Resonance is important, and I think that these would be good practice to go through your resonance structures. Eventually, you'll have completed your, what's up? So in this step here, we went from being attached to the enzyme to just being attached to one singular amino acid. And so our very general structure for carboxylic acid or for amino acids is this, where there's an implied hydrogen here. And so this hydrogen I just drew in from implied to explicit. Well, so the enzyme would have started as NH2. And so in forming our imine bond, we just wouldn't have done the final decarboxylation. That's because of physiological pH and the pK of those. I'm not sure. Yeah. In the first part, we're doing the imine formation with the protein. And so in our imine formation mechanism, we always start with a carbonyl and an amine. And in this case, the carbonyl is PLP and the amine is the enzyme. And then imine, imine formation occurs where we would lose that O, carbonyl oxygen, as water to form the imine. We're just forming the imine from the amine that was on the protein. Yeah. No. PLP has a bunch of steps to a mechanism. I don't think it would be fair to expect you to draw all of those steps in a time constrained exam. It's important for understanding what reactions PLP works with versus TPP. It does racemization and decarboxylation. Yes. PLP, when it's biosynthesized, has the carbonyl group. It then does the imine formation to the enzyme that will use it. And that is the way of the enzyme being like, I'm going to need you, I'm going to hold on to you. So then it will release it to do the chemistry, but at the end, after you've done your chemistry, the way that we release our amino acid and release PLP is by doing a transamination again back onto the enzyme. So the final step here. Yes. So it won't do the chemistry we care about until after it has already done the imine formation to the enzyme and the transamination to the amino acid pair. We need to know it for the reaction that happens after this. Yeah. Yeah. Yes. What's up? Yeah. I don't know. If you know that it deprotonates, then it shouldn't matter if it's given to you in the protonated or deprotonated form. But I'm not sure. Mm-hmm. Really just understanding where they will chemically use it. Like where on the molecule. What's that? Yeah. That is an abbreviated way of writing out a carboxylic acid. We're adding this whole part, well, really this whole part, which is an amino acid. Other questions? Okay. Once we have our PLP bound to the amino acid we're going to do our chemistry on, we will do the chemistry we care about. So in this case, I have it drawn for decarboxylation. So we can do the decarboxylation that gets us to and that anion is being stabilized by PLP. And so we can draw out all of the resonance structures that show just how far that anion can be stabilized. And once our decarboxylation is done, we can do another transamination that will get us back to this structure here, where PLP is now rebound the enzyme. And we have successfully decarboxylated our amino acid or racemized our amino acid. What's up? No. You wouldn't ever have to identify the amino acid. And if you would have to like the table of them. You don't have to memorize any amino acid structures, but know the like backbone where it's this general structure. Yeah. Mhm. Yes. So like with PLP, I would say knowing this nitrogen is where you're doing the transaminations. And originally it's this carbonyl group. And then once you have this carbanion formed, that's like this structure that I just circled, this one, is like the whole reason that we need PLP is to stabilize this carbanion. That does help. Is it the only part that helps? Okay. Yeah. An H. Other questions? Okay. The next one I'll talk about is CoA. I am not going to draw out the whole CoA structure because it's like very, very big. But you guys would have to do that in a homework assignment. The main part of CoA to know, though, is that it's an acyl group. It has a nucleophile. And so CoA will often see doing acyl substitution. That is really the main gist of all you need to know about CoA. The last one we'll talk about is ATP. I know that this one was covered in a homework and kind of threw people for a loop just because we learned about ATP a lot earlier than we learned about our other cofactors. And so we had learned about our other cofactors in like lectures 31 and 32. And ATP was mentioned in lecture 28. And ATP is used for amide bonds. We learned about it in the context of enzyme synthesis, how enzymes are built up from amino acids. And all of our little amino acids, they connect together by amide bonds. And so ATP is what is used to help those amide bonds form. So This is our abbreviated structure of ATP. And say we had some kind of amino acid here. It could tack here and push up on that oxygen. Where we get this intermediate that then will collapse and kick off two of these phosphate groups. So we end up with the two phosphate groups attached to each other. And then we have what's left of our ATP, which ATP is adenosine triphosphate. We've now kicked off two of our phosphates. This is a MP, which is adenosine monophosphate. And we basically have our amino acid kind of loaded onto AMP. What we can do now is attach our amino acid to the tRNA that helps us in the actual formation of our proteins. And we end up with well, actually, I'll draw it out. We can have the lone pair off of this alcohol from the tRNA. Tack our carbonyl. We make another tetrahedral intermediate. With the collapse of this, we can kick off the phosphate group. And we end with our tRNA bound to our amino acid. The main takeaway from ATP as a general cofactor is that it helps in the formation of amide bonds. What's up? Oh, so this would have like an O minus here. Which one? You're good. Third step, starting material or product. Over here. So the OH here. What's up? It's just there. That's a part of how we get from single amino acids to amino acid chains. It gets into more biology than we really need to talk about of like tRNA are transfer RNA that help code which amino acid, because you have there's a tRNA is there. That's a part of this reaction. There would be also a tautomerization here where the proton ends up on the phosphate. So we could draw it out in the middle. Where we have the phosphate that has the negative charge and take the proton. Don't worry about it. Okay. Do we feel better about cofactors? Do we feel worse about cofactors? I tried to highlight the most important of them. I'll upload this PDF. Yeah. No. Other questions on cofactors? Okay. I do think that this question is kind of covered by what I just did. Are there questions about that though? I had just mean like, so PLP can do decarboxylation and racemization. You don't have to draw both, but I don't want you to not think about the other one existing. So like draw one, but then say what the other one is. More an exercise in like making sure you know cofactors, less practice problem for exactly what would be on an exam. Other questions? Yeah. No, no. You don't have to memorize the structure. You should know what part of the structure is important, like if you recognize it, and you should know what reactions they're helpful with. Yeah. It's probably better to be able to recognize the reaction with a cofactor than like, because there's only one answer for that. Whereas if it's list out an example with this cofactor, there's a lot of answers for that. Mhm. What's up? Yes. PLP will be amino acids. TPP will always be when you have the two carbonyls next to each other. Mm-hmm. Yeah. Yeah. So with NAD plus, what kind of reaction do we expect to be catalyzed there? What kind of reactions do we expect with NAD plus? Oxidation. So if you saw this reaction and it was what cofactor do we expect? You can say, well, I went from an alcohol to an aldehyde. That's an oxidation. I only know NAD plus. With NADH, we know that those are reductions. So you look for the reactions that you recognize as reductions, which like an example of that could be a carboxylic acid to an aldehyde. With ATP, we know that we are looking for amide formation. Amide formation requires what two starting materials? I'm going to go more general than a ketone. So I'm going to say carbonyl. Because specifically with amino acids, we're not using a ketone, we're using a carboxylic acid. A lot of the recognizing reactions really lies in recognizing your functional groups. If you can recognize your functional groups and you know what functional groups you need for what reactions, then just by recognizing functional groups, you can start recognizing your reactions as well. PLP, what kind of reactions can we look at with PLP? We have a very specific starting material for our PLP reactions. Amino acids. And the product of those reactions will depend on what kind of reaction we're catalyzing. But with PLP, we really want to be looking for amino acids as starting material. Which of these reactions would amino acids be the ending material? ATP, as we hook our amino acids all together. TPP, what kind of reaction is it most known for? Decarboxylation. What motif in our molecules should we look to recognize? Two carbonyls right next to each other. Finally, what is our usual dead giveaway for CoA? A lot of CoA reactions, we'll see that we start with an acyl and end with our CoA bound to something. Bound to our starting material. What's up? Yes. Yeah. Multiple amino acids, like hooked together. I would say focus more on amide bond formation. Yes. What's up? An amine is NH, whereas an amide is next to a double bonded O. What's up? Yes, so you want the alpha keto acid, which means two carbonyls right next to each other. This carbon chain could be however long, but it's this part that is key. Okay, other questions about cofactors? Yeah, that's, yeah. Other question. Okay. Has anyone attempted the, oh, okay. Has anyone attempted this question? Can I get thumbs up or down? Okay. I'm gonna say take like 5 minutes and we'll check in at 5 minutes to start thinking about this question. Okay. So I've drawn out here the first steps of fatty acid biosynthesis. I'm gonna maybe go through this faster than, well, okay, I'm not gonna spend a bunch of time breaking down the chemistry that happens here because I already have a review video that covers fatty acid biosynthesis in pretty good detail. And it is the office hours video from April 16th of last year. But these would be our first 4 steps. Can we recognize step 1? And how can we recognize step 1? It's not an exact carbon copy of the things you have seen before, but it's somewhat similar. Close. If I replaced those sulfurs with oxygens, is it easier to recognize now? What is it? Claisen. We have become very accustomed to just doing Claisen reactions with esters, but we could also do them with thioesters, as we see here. So, does anyone recognize step 2? What changes in my molecule between the starting material and product of step 1, or step 2, starting material? What? Huh? Mm-hmm. Do we have a name for that kind of reaction? What is it? Reduction. What about step 3? Do we recognize what happened there? Elimination. And what about step 4? We have a fancier name for that. Other way around. Reduction. So we have our 4 steps identified. Do we know of any cofactors that can work in any of these kinds of reactions? Yeah? What kind of reaction? Yeah, a reduction. What kind of cofactor can we use in reductions? So how many NADH would we use in one full round of first fatty acid biosynthesis? 2. So, yes, NADH and 2. Do you guys remember what our starting material is called from our lecture on fatty acid biosynthesis? Hmm? That's what we'll make. Yes. So we start with acetyl-CoA and malonyl. Now, the next part is a little bit of math. If we did 4 rounds of fatty acid biosynthesis, how many carbons would be in our final product? How many carbon dioxide would be generated? How many TPP would be used? How many NADH would be? We'll work our way from the bottom up. How many NADH get used in one round? So how many would get used in 4 rounds? How many TPP get used in 1 round? 0. So how many get used in 4 rounds? 0. How many CO2 get generated? I haven't explicitly drawn it out. In 1 round or in 4 rounds? In 1 round or in 4 rounds? How many CO2 do I have created in just what I have drawn here? And in what step am I generating CO2? In step 1, because we'll lose this. So we only lose 1 per round. So how many would we expect after 4 rounds? Every round of fatty acid biosynthesis, we add on 2 carbons. So after 4 rounds, how many would we expect to have? 8 is not correct. In our first round, we have 4 carbons. Then we add 2, then we add 2, then we add 2. So we end with 10. In each additional round of fatty acid biosynthesis, we'll take this molecule and keep adding on 2 carbons. So in the first round, you start with 2 molecules that each have 2 that you join together. So your first round, you have 4 instead of 2. Every round after that, you only add 2 more on. Yeah. So this is only showing 1 round. Yes. So at the end of the first round, we would start with this one, and then we would keep adding on until we get like I think we add on malonyl CoA every time, and that's why we lose carbon dioxide. But you're either adding malonyl or acetyl. So you'll add 1 more of. Yes, basically just every additional round adds 2 more carbons and uses 2 NADH. You don't have to know where it comes from. You would never have to like draw this from blank. No. But knowing these steps in general, not like the breakdown of the methods. What's up? Do the mechanism. So we know that Claisins are done with esters normally. And in class, we talked about how fatty acid biosynthesis, we start with these 2 thioesters, and we can do a Claisin-like reaction using the thioesters instead of the esters. It's not an exact like carbon copy for the Claisen reaction, but it's similar to the Claisen. Yeah. Yes. So in the like older office hour video I have on it, we kind of depict it as machinery, where you can think of it as like a square, and you'll do the Claisen-like reaction, then you'll do your reduction, the elimination, the reduction, and then as you continue to do rounds, you keep going around the square. Any other questions? Yeah. Um, it could be, yeah. It could be a more advanced form where you already have something that has like undergone a few rounds of fatty acid biosynthesis. And this is showing like the 5th round, but I have drawn out here just the 1st round. What's up? What your starting material is. So you'll either have something that has a bunch of carbons already, or you'll have this malonyl CoA. And then every time after, you are adding the acetyl CoA. Yeah. Yeah, so you like won't have to do like full mechanism of fatty acid biosynthesis. The important steps, yeah. Yeah. That would be something to know. Yeah, so you have like the starting materials, then you have the diketone. Well, it's not really a diketone because one is a thioester. And then you have the OH, the double bond, and then the fully reduced. Yeah. Mm-hmm. Well, so you would start counting with how many carbons are in your starting material. So if you started on like the 2nd round, instead of malonyl CoA, you would have something that has 6 carbons. And then you would add on the 2 carbons from acetyl CoA. Yes? No? If you had already done 2 rounds, you would have had 4 carbons from the 1st round and 2 carbons from the 2nd round. So then your 3rd round. Yeah, so it would be like this. The CoA part of it, side of it, is what attaches to like this machinery that goes around. Any other questions? That is the last question that I had prepared for you guys to work out. What's up? Usually it's pretty fairly split. Any other questions? Yeah, what's up? Well, so you're always going to start from electrons, and those will most often be found in a lone pair or a pi bond. Most often, it'll be from a lone pair. Any other questions? That is all I have for you guys. If you have any questions that come up between now and the final, you can feel free to email me. Good luck. Hope you all do well. It was nice knowing you guys. Bye forever.